we are going to show that the complex exponential function is periodic. In order to see this, just add 2 pi I to the argument set. Set is equal to x plus iy, and we can here collect the imaginary part, and we obtain this. Here we see that we have the exponential function of I multiplied with y plus 2 pi, and this additional I 2 pi does not contribute anything, so we can remove it, and we obtain this, which is the same as the exponential function of set. So this shows that the exponential function of set plus 2 pi I is equal to the exponential function of set. So the exponential function is periodic with period 2 pi I. Well, let's turn to some task. Why is this function entire? That means analytic in all points in the complex plane. And this is a very simple task, because we can differentiate this function, and then we obtain this. It's very easy to differentiate. This also is a constant, so the derivative is 0. This is just a product of a set which is differentiable with another differentiable function, which is the exponential function, and this function is just a composition of minus set, which is differentiable, and the exponential function itself. So this is possible to differentiate very easy, and in fact here is the derivative of this function. So this shows that the derivative exists for all set, and this is by definition means that f of set is entire. Let us show in the next task why the function, this function, is not analytic, the exponential function of the conjugate of set. We want to show that it's not analytic in any point in the complex plane. And the way of doing it is to use the Cauchy-Riemann equations. So we know that set is equal to x plus iy. So this can be written in this way. And well, after some manipulation, we obtain that the real part of this function is just the exponential function of x multiplied with cosine of y, and the imaginary part is minus x minus the exponential function of x multiplied with sine to y. Using, or first finding the first order partial derivatives of u and v, we get them very easily, and here are the results. And now we are checking the Cauchy-Riemann equations. This is the first Cauchy-Riemann equation. If this should be this equation should be fulfilled, then this must be the case. And if this is the case, well, then we have that cosine of y should be equal to 0. That's pretty easy to see, because both these two functions are different from 0. So if we take this function, or maybe take this function on the other side of this equation, we get 2 multiplied with the exponential function of x multiplied with the cosine of y. And this should be 0, and the only possibility is that cosine is 0, because the exponential function can never be 0. So in order to get cosine equal to 0, we have to y must be equal to pi over 2 plus some multiple of pi, integer multiple of pi. Okay, that's the first Cauchy-Riemann equation. It can be fulfilled if this is satisfied. Let's see what's happening if we assume the second Cauchy-Riemann equation. Then we obtain this equation, and in the same way we conclude that sine to y is equal to 0, which implies that y should be 0 plus some integer multiple of pi. And it's not possible to fulfill both these two conditions, so we can conclude that Cauchy-Riemann equations are never satisfied. This means that the derivative of z does not exist at any point, and f is trivially not analytically. Well, let's take another task. Here we have the absolute value of the exponential function of 2z plus I, and we want to take the absolute value of this to write some expression of this, and we also want to write some expression of the absolute value of the exponential function of this guy and we want to write it in x and y, and use this to show that this inequality is satisfied. In order to do this, well, we just do as above. We replace z by x plus I y, and it's rather easy to see that this reduces to this. And now we are on the form on the polar form, where r is the absolute value, and here we have some exponential function of I and some angle here. This means that this must be the absolute value of the complex number here. So what we can conclude is that the absolute value we are trying to describe is equal to the exponential function of 2x. In a very similar way, we find an expression for the exponential function of I multiplied with the square of z, and we obtain this expression for this. Or we obtain this absolute value in the same way as above of this guy. So, okay, let me go back. So, well, now we have done the first part of this task, and now we are going to prove this inequality using the the triangle inequality, we obtain that the sum of these two complex functions, the absolute value of it is less than the absolute value of the first, and the plus the absolute value of the second. And we know we have some expression for this. We have expressed these absolute values before, and we obtain that they are equal to this sum. So then we have reached our goal. We have shown this inequality.